Okay, so let us start experiment number 7, image formation of the lenses. Okay, so we're going to use this simulator. All right, now this simulator we used last time also. So the first thing is that you can see different options: file, tools, views, and the settings. On settings, just click on the grid. When you click on the grid, okay, when you click on the grid will appear, and then zoom in into 200 level. Then we can see it a little bit clearly. Okay, then we'll start making the ray diagrams, and then we're gonna get all the information extracted from the ray diagrams. Okay. All right. So now the first one is creating the ray diagram for the double convex type lens. So the double convex lens will do the converging. So to do that, we first need the meter ruler. So let's do the meter ruler here, and then that will act as a principal axis. Okay, and then you need to just click on one end and then click and drag to the other end, and then the numbers on this ruler has no any meaning. um, Technically we can consider this 100 is 100 millimeters. In that case, each of the least count for this meter ruler going to be about 1 centimeter. Okay, which means I can estimate all the way down to 0.5 centimeter level. All right, now let's start making the lens. Now, if you want to make a lens, what I need is the glasses right here. You can see different options on there. Use the ideal lens. If I use the ideal lens here, and then if you click on one point right here, then you will see an arrow, red arrow, and then drag downward direction. You will see that midpoint has a small white line, midpoint of the lens. That white line should be exactly aligned with the principal axis. When that is exactly on the principal axis, click again. What principal axis does generally divide the lens into two segments, right? So that's how it is exactly right now. Now, when it comes to lenses, there's two types. One is converging, other one is diverging. Converging type must have to have a focal length which is positive. So now you can see here, it says the focal length on the very top. So if we can put that numbers randomly, any number, but let's do like about 60 there. If I do 60 there, which means this measuring in like pixels, okay? So that 60 going to be about like 6 centimeters focal length for this particular lens. Right now, the first step is that identify the focal length by using the ray diagram. Now to do that, what we need is the parallel rays. Any parallel optical ray which is parallel to the principal axis, after refracted through the lens, should be converged and then pass through a certain point on the principal axis. That point is considered as a focal length, right? Now to do that, I need at least a couple of parallel rays. We can do it by using this beam right here, but instead we'll draw rays. Okay, so now if you click on the ray right here on the tool menu bar, and then click on anywhere here, just one click, then you will see a dot appear, large red dot. And then if you click and drag, then you will see a ray and then another red dot, right? So you have to realign this red dot, the second red dot, until that yellow line, incident ray, which is exactly parallel to the principal axis. When it is exactly parallel to the principal axis, you can see refracted ray crossing through a certain point. That point is the focal point. Now to measure that, what I need to measure is how many number of segments on this meter ruler. Now, if you take a look right here, this is where the lens is. We're measuring from the midpoint of the lens, right? This red arrow, that pointer should be on this vertical line, right? So 1, 2, 3, 4, 5, 6 segments. So 6 segments mean we are using 1 centimeter per segment. It's about 6 centimeters, right? So that's the idea. If you put the lens, that value, if you click on the lens, that focal length appear, that 60 means about 66 centimeters on focal length. Let's do at least one ray. Then we can identify let's do that ray on the down this side of the right here, bottom from the principal axis. Now after it passed through the lens, you can see that should cross exactly the same point. So that's the idea of the focal length. Now when it comes to the lenses, you can observe the lens from any direction, right? So if the object is to the left, if you're observing from the right, then the focal point is on the right. But I can do the same, but oppositely. I can place the object on the left, I can place the object on the right, and then I can observe from the left. Then if I'm observing from the left, then the focal point should be on the same side as the observable side, right? So let's check that out. So let's draw another ray starting from the right side right here, and let's realign to parallel that ray to the principal axis. You can see after it refracted, it crossing through a certain point. Now I'm observing from the left. You can see that cross exactly 6 segment away from the lens. So that is about 6 centimeter point. Okay. So let's do one more ray. It is exactly the same way, parallel, and then after it refracted, it crossing through the same point, right? Now, technically, lens can have the focal point on the both side depending on where you're observing. Okay, always we're going to observe other side relative to where the object is, and then depending on that, we should be able to draw the ray diagram. Doesn't matter which side is the object is. Okay. Now that just to identify the focal length by using the ray diagram, you can take a screenshot of this, and then all those screenshots now in this particular lab is actually considered as a data, because that's important part, because we're going to extract all the data from this ray diagrams. Okay, so you have to input that data for the convex type lenses on table 5 and the concave type lenses on the table 6. Okay, so let's insert that into here. Ray diagram for the focal length. Crop that out, anything unnecessary. Just need only this part to show nice ray diagram. This part. All the parallel rays converge into one point, that is the focal point. Okay. Right, and then realign that, change the size until it nicely fit into this area. Okay, now let's do the ray diagram by changing the object location. Okay, now to do that, you can use the same lens with the focal point is about like 6 centimeters. Let's keep the same lens, and then I can get rid of we just need only 2 rays to identify the object. Okay, so let's make the object somewhere on left hand side. So to make the object, you can use a ruler and then click on the ruler and then draw object. Now this lens has about 6 centimeter focal point. I have to have the object about more than twice the focal point distance. Okay, so which means that should be about like 12 segments. It should be more than 12 segment away, right? You can move this lens into a nice location like this one. Now it is on exactly this point right here, that midpoint. So that point to 200 is 5 segments, 10 segments, 12 segment right here. So let's place the object somewhere at 100 level or a little bit below, beyond that, okay? So this is the 12 segment location. So let's place the object right here, further away from there. So somewhere right here, much further away. And then draw a ruler. The size should be about like 4 segments. Then we can consider the height of the object is about like 4 centimeters. Okay. And now it is how much segment away? This is 5, 10, 15, 20, 21 segments away. So which means 21 centimeters away from the lens. Okay. Twice the focal length is just 12. So we can take 2 data point above the focal, above the twice the focal length, 2 data point in between, and then 2 data point below. Okay, so we just need about like 6 data point to make the graph. So let's draw the ray diagrams. Can bring maybe a little bit closer here. Like, let's place it here because I need a little bit of space to this side too. So then it's going to be 5, 10, 15, about now 19. Place exactly at 18 location. Okay, doesn't matter, you can place anywhere. So now I need 2 rays, right? One ray should be passing through very top of the object and then hitting the lens exactly parallel to the principal axis. That should pass through the focal point other side. Then I need another ray. There are a couple of options. You can do that ray passing through very top of the object, and then it is passing through exactly the vertex point of the lens. If that is the case, that ray should be passed through without any bending, right? So that's second ray. Whenever the 2 rays are meeting each other, we can identify where the image is, right? Now image is right here. So let me share that. So let's make a ruler right here to point out the image location. Now you can see image is around this location, and the size of the image is about like 2.5 roughly. We have to estimate now this half the centimeter point. Okay, if it is close to half, we should do 2.5. If it is not, we should do 2.0. Accordingly, we will get a little bit of error. That's okay, totally okay. And also this, when we measuring the in between these, you can see now image location is very close to 2.5, not 2.0. So we can estimate that to 2.5 also. Question. Okay, so let's measure everything. Now, what you have to take the screenshot of every or each of these cases. Okay, one screenshot, and also you have to have the data into table number 1. Now, the focal length we actually doing here about 6.0 centimeters, which means 0.060 in meters. We can estimate the next decimal place. Reason I can estimate half the centimeters. Okay. Now object position, we're going to measure in unit meters, image, unit meters, focal length, we will calculate in unit meters, magnification we'll calculate later, and then we'll compare those two. Magnification we can do by using the distances and the heights, okay? And the height of the object also you should add here. So the height of the object right now, we are actually using, let's add 2, focal length of the lens and the height of the object. Okay, so now the object is at 5, 10, 15, 17 centimeter location, so which means 0.17. Image is at 5, this is 10 location, this is 9, so you can estimate to 9.5, so which means 0.095. Now you can see You have to record all of these numbers to about like 3 decimal places, right? So let's reformat this into 3 decimal places, all the numbers. Okay, let's calculate the focal length for that one to see what we can, what we getting. Equal sign, parentheses, 1 over d0, close bracket, plus 1 over di, close bracket, twice power minus 1. We're getting about 6.1 centimeters, and then we're expecting about 6 centimeters. That is good, right? So also let's add the height of the object that we know. Height of the object, we're going to keep it constant. That is about like 4.0 centimeters, 0.040 meters. Okay. Now all you have to do is actually slowly decrease the position of the object location, and then extract all the data. Okay, and also you need the size of the image, right? So that also you need. Okay, size of the image is about like we can estimate 2.5 centimeters. Okay, 0.025. Okay, let's do the magnification also. Magnification equal sign di over d0 negative di over d0. And for the image is actually, you can see towards the negative side. If it is inverted, image height we have to record with the negative sign, right? It's negative 0.25 centimeters. Magnification from the image going to be equal sign. Image height divided by object height going to be always the same, 0.04. So getting the magnification from the distance is about like 559. Magnification from the height of the image over height of the object, which is about 6.2 centimeters. There's a little bit of error there. That makes sense because we actually estimating this one. It may not be the right number. To test it out, you can just check that if I use 2.0, what will happen, that will be the same amount of error, because we cannot estimate in between anything other than zero point 0.5 centimeters. Okay, because of that, that estimation usually will provide fairly large error. Okay, but that's okay. So we can estimate this into either to 2.0 or 2.5, doesn't matter. Amount of error going to be about the same. Okay, so let's do percentage error here, comparing those two. But the distances will be more accurate than the height. I think equal sign ABS parentheses, doesn't matter which goes first, we'll do percentage difference. Okay, so the percentage difference, first one minus the second one, divide by ABS, the first one, multiply 100. Okay, so ABS parentheses, magnification from the heights, close bracket, multiply by 100. So it's about little bit of high error because of our estimation we're doing here. Okay, right, then let's continue. Now also you need a screenshot of this one. All of those screenshots should go here. Okay, table number 5. So you have to have a 6 screenshot for 6 different data points. Cross out anything, crop that out, anything unnecessary. Okay, so that should go here. Now we are working on object distance is much larger than the r or twice the f. Okay, say here r or twice the f. R is not much meaningful, twice the f is much better. Okay, then all we have to do, click the object and then drag maybe still D should be above the twice the focal point level. The focal point times 2 is about 12 centimeters, so that should be about here. Let's move this one about like 3 segments right here. Now the parallel line, you can leave it like that. Only thing is changing is the other way, right? You can just realign that. You can see the image moved, right? So there I have to move the image into here now. And then accordingly, the length of the image also changes. I have to expand this length right here. Now let's take a new screenshot. And then I have to add the data into here. New object location is about 510. This is 14 centimeter location, 0.14. And the image position is, this is 5, this is about 10, this is between 10 and 11, so we should do that to 10.5, 0.105. Let's do the focal length calculation to check how much accurate. That's perfect. Accuracy is good. Image height changes. Now it's 1.34, about like 4, about 3 centimeters, right? 1, 2, 3, 3 centimeters, which means negative 0.03. Let's check the magnification to check the accuracy. So it's fairly good. So depending on our estimation, you can see some places we can do very good accuracy. Some places we're going to have a little bit of error. Okay, that's totally fine. Let's add that into here. This is the second image, secondary diagram we need when the object is beyond the twice the focal point level. So that out, anything unnecessary. Sure image, and then all the rays are visible, object, and then the lens and everything. Okay, so that goes to here. Right, then let's continue. And then we'll bring the object much closer in between focal point and the radius of curvature level. Radius of curvature is at 12 right here, so let's bring it into position of 10. Okay, if you click that and drag it into here, that is about 10 centimeters away from the lens. Parallel line, you can leave it as it is. Just need to change this line right here. Second ray. Now you can see image is much further away. Much further away, and then getting much bigger now, right? So now let's take another screenshot. Let's add the data into here. Now third position is about 10.10. Now image is at 5, 10, 15, and in between 15 and 16. So let's say 15.5155. Let's calculate the focal length. Very good number. And the image is now about 6.5 centimeters, negative 0.065 in centimeters. Let's do the magnification to check it out. That fairly good. Error is about like 5. Okay, then let's change the object to more segments to the front. Two more segments to the front. Let's change this way. Parallel ray, you can leave it as it is. And you can see now image moves much further and then getting much bigger in size. Now it's right here. Okay, now object is at about 538 centimeter location, 0.08. Image is at now, we have to get a screenshot also for this one, okay. Now this is 5, 10, 15, 20, about 25 centimeter location, 0.25 centimeter location. Let's check the focal length, good. And then image size is now 5, 10, 13 centimeters, but negative 0.13, it's much bigger. Let's check the magnification. Good. Okay, so let's add those two tree diagram also here. Now the object is in between the focal point and the twice of the focal point limit. Okay, twice the focal point limit. Insert. Two ray diagrams. This goes here. And then we need to change the size of the pictures to match with this amount of space. Tree diagram. Okay. Now let's do two more data point. When the object is much closer, very much closer, then we have enough data points to do the graph. Okay, two more data points is enough. So let's bring the object much closer, closer than the focal point level. Focal point is 6 centimeters. So let's bring it to like maybe about 5 or 4 centimeters level. Okay, 4 centimeters away from the lens. Right there, the parallel ray you can leave it as it is, and the other ray you can realign. Now you can see the other side of the lens, these two rays will not intersect, so which means image will not form here, image going to be formed the other side. So I have to extrapolate the rays. So to do that, you can go view and then click on the extended rays. When you click that, you will see orange color lines appear. Those lines actually intersect here. That's where the image should be now. You can click this next meter ruler and then bring it into here. Or you can redraw meter ruler from here. This is where the image top point, from there to the principal axis. That's where it is. Okay. Now we can see, let's take a new screenshot. Now image is inverted, image is upright, and then it's virtual because it is resulted due to this extrapolated rays, right? Let's add the data into here. Now object location is about 0.04. Because the focal point image distance now negative because it extrapolated rays. And the location is about 5, 10, this is 11, in between 10 and 11, we should do 0.1 of 5, like 10.5, it is not exactly 11 either. That's a little bit of error there on the focal point, that's okay. Image height is now about 5, 10, 11, but it's positive now because it's upright, right? So you can see magnification, very good match. Let's bring it a little bit closer, the object. We can do 3 data point if we want to here, but 2 is enough, I think. Let's bring it to about like 2 centimeter location. The parallel ray, you can leave it as it is. And the other ray, you have to realign. To realign that, you can see extrapolated ray is actually meeting right here. Then you have to bring this meter ruler and then put it here. Now you can see object size getting smaller and then it getting very closer to the in size and the place board getting much closer to the object location, right? So let's take another picture here and then add the data here. Now the object is on 0.02, image is negative 0.03. You can see this is perfect number for the focal point. Image height is 6.06 positive. Now that magnification is perfect. So we have about like 6 data point. I think that is good enough for the graphing. So this part we can leave it empty. That's okay. So now let's add those two graphs into here. Insert those two ray diagrams. I think I did not take the picture of the other ray diagram. I can just quickly redo that. Okay, let's quickly redo that. Previous one. It should be at 4 centimeter location. Okay, so images. Do that very quickly. Okay, so let's make a graph now. So we need the graph between 1 over di and then 1 over d0. Okay, to make the graph, we need two more columns added here, 1 over d0 and 1 over di. Let's calculate that 1 over d0 and 1 over di. The graph should be 1 over d0 versus 1 over di. By using the intercept of that, like you done for the last experiment, we can find the focal point. Okay, so let's insert the graph, scatter plot always, add the data, and x should be 1 over d0, y should be 1 over di, and it should be nice linear graph. Let's add the chart title, 1 over d0 versus 1 over di versus 1 over d0 for convex lens. If you have a graph, chart elements, we need the axis title, both axis title, and then we need the trend line linear, right? If I have a trend line linear, I need to have all these last two options clicked because I would like to see the equation, but don't click the set intersect into 0 because this intercept is not 0. Okay, and axis title x 1 over d is 0, units 1 over m, axis title y 1 over di, units 1 over m. Okay. And we know the intercept is 16.385. From that, we should be able to calculate the focal point. Let's do it here on table number 2, focal point analysis. So we have the focal point calculated earlier on table number 1. We can take the average equal average, and focal point we calculated earlier on cell numbers F10 to 15, about 0.061. Let's do the PE equal ABS. Expected value is 0.06. Calculated average is about on cell number C23. Close bracket, divide 0.06 multiplied by 100, about 1.93. From the graph, that should be inverse of the intercept, equal sign 1 over intercept of the graph in this equation 16.385. 16.385, and then you can drag this. You can reformat all these cells into about 3 decimal places. Okay, so it's a very good number. All right, so we done all, and then we need to name this graph. This should be now figure 1. This is graph of 1 over di versus 1 over d0 for convex lens. Right now, in the next part, we're going to investigate the same thing, but we are investigating same ray diagrams, but for the concave type lens on table 2. That's the plan. Okay, now in this case, we want to change the lens into a concave type, which means diverging type. Now let's get rid of these rays, and also we'll get rid of this rulers. The meter ruler and the lens, we can keep it as it is, nothing gonna change. Only thing is changing is the focal point, right? Because if I put the focal point into negative 60, then you can see that red arrow direction changes automatically. That direction change automatically adjusting the lens into now diverging type. Now to confirm that, I need the ray, right? Let's draw parallel ray and then take a look what will happen. If I start from there, and then if I draw a parallel ray, you can see that ray now diverges, right? If I click the extended ray, extrapolated ray, now you can see crossing on this point, there is about 5 segments from the lens. So now the focal point is negative. Focal point is same side as the object side. There's no real ray passing through there, so that's a negative focal point. Let's draw one more ray to confirm that. Here, like we done from the last one. And also focal point should be on the other side too, right? Depending on where the object is. So we can do 2 more rays from here, then we can confirm the focal point on the other side also. From here. So now the focal point is other side 6 centimeters away from the lens, right? Let's take the print screen, that is just to confirm the focal point. Now we're doing the focal point for this particular lens is about minus 0.06. Okay, and all those ray diagrams should go into table number 6. Let's insert that into here. should go here. Okay, then let's do the same thing by changing the object location. Let's draw the ray diagrams and then extract the data for our table number 3. Table number 3 should be, this should be table number 3. This is focal length and image formation for diverging type lens. Okay, diverging means double concave. Okay, so let's continue. We can get rid of these two rays, and we need the extended rays always for this case. Let's draw a object in the ruler. We can use the same numbers as we done earlier because we are using the negative of the same number for the focal length. So we can use the same numbers we done for the D0 earlier. About 17 centimeters away, 5, 10, 15, 17 right here, and then about 2 squares high, 4 centimeters in our meter ruler. And I need the parallel ray. Should be hitting parallel to the principal axis. Diverge, extrapolated through number 6 location. And we need one more ray that we can do directly hitting with this point right here, or there's another way to do this. If I bring this ray, it should be look like try to go to the focal point on the other side. You see that this dot I'm bringing to other side exactly number 6 location, right? That is the focal point on the other side. If that ray, second ray, try to go to that focal point, which is coming exactly top of the object, you can see that ray after refraction becomes exactly parallel to the principal axis, right? That is opposite of the previous ray. Whenever two extrapolated rays are meeting each other, then you can identify it. Now let's draw the image right here. It should be very small now. Draw maybe here and then click and drag that into there. Let's click and drag. Click and drag into here. It's about like 1 centimeter in height. Okay, not more than that. It's very difficult to draw right there. I draw the second meter ruler away and then click and drag. Okay, take the screenshot. And the image distance is about 1, 2, 3, 4, about 4.5, but negative, right? Negative 0.045. You can do 1 over d0 because we need those for the graphing purposes. 1 over di. Let's calculate the focal point. Equal sign parentheses 1 over d0 plus 1 over di power minus 1. It's about right? We're expecting negative 6, but we're getting negative 6.1. Image height is now upright, positive, about 1 centimeter, 0.01. Let's do the magnification. Equal sign minus di over d0. Okay, so let's do the calculation for the magnification from the height here. Check that equal sign hi over h0. H0 is always about 4, right? 0.04. So getting about the same number. Let's compare them. Equal ABS parentheses magnification from the distance minus magnification from the height. Height 33 divide by, let's do PD for this one, right? These double brackets, magnification from the height is 33 plus magnification from the distances and height is and I33 divided by 2 close brackets multiplied by 100, about 5%. Here also we doing we should do PD actually. There's no expected value there. So let's do PD instead of PE, both of them. It should be then plus 5 divided by 2 and same number almost. There's nothing changes, but the PD make more sense there because we don't have any standard or expected value like the focal point. We're just comparing these two. Okay, so because of that, let's do PD for that. Okay, now let's continue. All right, so all we have to do now, change the object location and then repeat the procedure. And then we have to get the picture for every case, right? All those pictures should go into table number 6. I need pictures, like 2 pictures for each case, okay? When the object distance is larger than twice the focal point, and then in between focal point and twice the focal point, and then below the focal point. Okay, let's bring the object to about location of 14 centimeters. You can drag this one. This is 5, 10, 14 centimeters right here. Parallel ray, you can leave it as it is, only I have to realign the second ray. It should be look like hitting the other side of the mirror. Try to go to that point, but it becomes parallel after refraction. You can see the object image location slightly changed, but nothing much at all. And the size also slightly changes, but nothing significant. Okay. Can't really estimate even to 1/2. It should be estimated to 1.0 probably, I think. So let's do that object image distance now negative. Image distance now very close to about 4 centimeter location. We should do now 0.04. Let's check the focal point calculation. We have a little bit of error there, but it's okay. Height we should do, height is about the same. We can't really do any estimation. 0.01 itself. Let's check the magnification. Too large error there. The reason is actually that estimation, right? We can't estimate that correctly. So that will give you a little bit of height. Okay, so all we have to do, let's take another diagram, another picture here. I should go to this one right here. Almost the same, similar pictures now. There's no much difference in this diverging lens. You can see the object is always virtual and then stay between the lens and the focal point location, right? So let's bring the object much closer to about 10 centimeter location. Click and drag 10 centimeter. Right here. And parallel ray, we can leave it as it is. The other ray we have to realign. If I realign the ray, now you can see object image is slightly shifted, but not anything significant. Right? See, I can now able to measure down to maybe 1.5 magnification if I take a picture of that. And image location is now minus about still like 0.04. So that's where the error going to be happening, because we can't estimate anything beyond the 5 centimeter point, right? So that's why a lot of error is actually happening there. And the image height I can do now 0.015. Let's take a look at the magnification. Because since image is moving very little bit, it's very difficult to estimate that is small changes here. Okay. And that picture should go here. These diagrams are almost very similar to each other. Okay, then let's bring the object much closer to about to about 8 centimeter location, 5 to 8. You can see nothing much actually happening. Image will become slightly larger, but it's very difficult to even measure anything. It's not even 2, but it's closer to 2 centimeter point. One more picture. Now the location is in between 4 and 3. We can estimate to 3.5 centimeters negative. And we can calculate to check focal point is fine. Magnification is close to 2. Let us assume to 0.02, and then let's check how is the magnification. Error is fairly considerable. Okay, that's okay. That because of the estimation issue, because we can't estimate anything below 0.5 centimeter level, so that creates a lot of error. Okay. Okay, now let's do that picture here. Same pictures, because in this case image is not changing much at all. So the ray diagrams, you can see the difference between the previous ray diagrams and the now. All the ray diagrams are very similar. There's no difference at all. Let's bring the object much closer to see what will happen. Now we are bringing the object almost beyond the focal point limit. So let's bring it to about 4 centimeter location. Keep the parallel ray unchanged, and then let's change only the other ray. You can see now the image become a little bit larger now. Let's draw another ruler here to identify the image. And now the size is about 1 to about 2.5, right? Let's take a screenshot. Let's do the data Here the position of the image is now very close to 2 and 2.5. Let's do negative 0.025. That estimation creates a lot of error. Okay, so that has a fairly considerable error. And the height is about 2.5, 0.025. And then that magnification is better because that estimation is exactly in between 2 and 3 lines, right? So that's the idea. So let's add that picture also here. Okay. With one last data point, let's bring the object much closer. It should be now at about 2 centimeter location. 2 centimeter location, then this ray should be much further here. Okay, now you can see images right there, very closer to the location of the object, and the size is only slightly less now. Object getting much closer to the size of the image itself. This image is getting much closer to the size of the object itself, right? Let's add that picture here. Okay, so let's do that last calculation here. Now the image location is about between 1 and 2, negative 0.015. Let's do the focal point calculation. That much better answer. Magnification is very close to 3 centimeters, 0.03, and then magnification is much better because estimation is much better there at that location. Okay, now let's make the graph and then check the focal point by using the graph. So you can make a new graph or you can actually copy paste this graph. Make a copy of this and then paste into here because it's the same graph. We just need to do the data, right? We redo the data. This is figure 2. This is for the concave lens. Okay, so let's edit the data, right? So to edit the data, you can just double click on the graph, then select data, then series 1, then click edit, then delete everything on X, and then add the new data for X. That should be 1 over D0, but on table number 3. And then delete everything on the Y. Y should be 1 over DI, but on table number 3. Click OK, click OK again. So now we should have a slightly different answer than previous. You can see the focal point should be inverse of the intercept. Earlier I got about 16.385 positive. Now I am getting negative because this should be a negative number, right? Focal point. So that's important. So let's do the focal point analysis. Average from the previous equal average function. We calculated focal point here, table 3. And then let's do the average of that. About good. And then let's compare with the expected value is -6, minus calculated value is C47, divide by ABS parentheses minus 0.06. Okay, because it should be in meters unit, close brackets multiplied by 100, about 3% error. From the graph equal 1 over parentheses minus 16.191. So now you can see, let's do about like 3 decimal places for all of these calculations. So it's very closer compared to the average we got, and the number we're getting from the graph almost the same. Okay, so now the last part of the lab, what we're going to test it out is the combination of lenses, right? To test the combination of lens, all you have to do, a combination of lenses can be used for different application. Two important application is the microscope and the telescope, right? To do that particular situation, we need to get rid of the objects here, and the lenses should be in that case always converging type lenses we need for that case. Okay, converging type lenses. And I need two lenses, right? This is lens 1. You can draw another lens, go into lens, ideal lens, draw another lens that about like maybe 11 segments, 11 squares away from the previous lens, and then change the focal point of that lens to maybe like 100, 150. Let's take a look. A little bit. Let's do 160. Other one is 100, and we'll keep about like 80 squares separation between the two lenses. Okay. Okay, now if I want to do the microscopic behavior, so in terms of microscope, what it does, it actually try to observe the object which is very closer, right? So I need the object much, much closer. So let's do object little bit away from the 6 centimeter location, little bit away from the focal point, but it should be about that range, right? This is where the focal point is. Let's place an object little bit away, like maybe 7 centimeter location or 8 centimeter location. Okay. Let's do one parallel ray. Hit the lens number 1, and then other ray as usual, which passing through the top of the object, and then that should hit exactly the vertex point of the lens. Then that ray you can see passing through without any bending, right? Now you can see that is actually building an image right here in between the lenses. To make this object little bit smaller, more smaller, we do 1 square in size. Yeah. So because we try to observe usually extremely smaller objects by using the microscope, right? Very small object. Now this is the first image right here, right? Usually what the microscope does, it actually need to make magnification, right? So the magnification is the most of the important thing for that one. Now you can see, depending on where I place this second lens, I can actually make the final image much bigger in size, right? So let's do a little bit elongated this one. Now you can see if my Okay, let's do this object is about like 80 squares away from the lens. So which means 448 away from the lens and the parallel ray and the secondary ray. Now you can see the image is actually about right here, very small. Now I can use a secondary lens to actually produce a larger image of this secondary image, right? You can see depending on where I place the second lens, you can see the virtual image I can produce, but much larger in size, right? Let's draw this a little bit larger to see the effect clearly. So I can use maybe that much height. Okay. Now the first image from the object is right here. That should be the object for the second lens, right? So the final image you can see producing here. So let's place this around 3, 6, about 8 segments away. That's totally fine. Then it will identify the, let's draw the ruler here to identify the image. You can see now image is fairly small still. And the final image now you can see much bigger right here. So it's much bigger compared to the object, almost twice the size of the object. So the likewise, we can actually rearrange, redo this by changing the object place and the second lens place, and then accordingly we can actually produce much bigger image. Okay. So that's the idea of the arrangement, which, okay, let's take the screenshot of that. And let's do the telescope view here. If you want to do the telescope type lens combination, then I have to consider two rays coming very further away from each other. So that means these two rays is actually come from infinitely long object away from infinitely longer distance. So that means every ray hitting the lens number one will be actually parallel to each other. So we can consider these are the two rays which are parallel to each other. Now when these two rays are crossing through this lens number one, you can see after it crossed through, it will produce an image. That image should be exactly at the place of focal point. So that's how we can identify whether I'm observing the infinitely long object or not. You can see that should be these two are crossing exactly at the focal point, and the image is extremely small right now. Okay. Now what we can do by using the secondary lens, we can actually produce image of this image number one. We can actually magnify by using the lens number two. So that's the arrangement similar to the telescope arrangement, right? So now you can see I have a fairly larger image right here. Doesn't matter which side it is, we can actually change the inversion and then get the image into this side too. You can see if I rearrange this position at a certain point, I can get the image into the other side also. That's not important actually, but really important, both of these telescope and the microscope is actually observing the object which is much further away. And then the magnification is so important part. Okay, question. All right, so we'll take a picture of this one. And that's the arrangement similar to the telescope arrangement of two convex type lenses. Take a picture of this one, and then those two pictures should go here. Okay. So similar to the microscope arrangement, telescope arrangement. Object is coming from the infinity. Then I have two convex lenses and then observing the object which is similar to the observing infinity, right? So that's arrangement similar to the telescope. And then when I observe the object much closer, then that is similar to the arrangement of the microscope. Okay, we're not really studying those two, just checking how the lens combination can produce those two particular cases. Okay, so let's crop this out. Now I'm observing object much closer, but the magnification is actually what we're more interested there also. So let's do images should go here. Right.